Okay, here's a quick video reviewing the major points about springs. Obviously, if we have a spring, a force is going to be necessary to stretch or compress that spring. Let's say there's a block here attached to the spring, causing it to stretch this much over here. And so I can label that force as the force of gravity, the weight of this block. Let's just say that that's 2 newtons. At this point, the block is in equilibrium, which means the spring is pulling up with an equal force. We'll label that as F sub S for the force of the spring on the block. So that's also going to be 2 newtons. We're going to be dealing with ideal springs, which means that the force provided by the spring will always be directly proportional to the change in length of the spring. So what does that mean? Let's say we start off with this spring with an initial length, xi, of 0.3 meters. We hang the 2 Newton weight from the spring, and the new length of the spring, xf, is 0.7 meters. We don't really care about either of these values. What we care about is the change in length of the spring. So that's this value from here to here. That's delta x, and it's going to be equal to 0.7 minus 0.3, so we get 0.4 meters. So we are making the claim that the force of the spring is proportional to the change in length. This just means that if I were to double the force on the spring to say 4 newtons, I should expect that the change in length of the spring should also double to a new length of 0.8 meters. And we'll demonstrate this in the simulation in 1 second. So these two variables are very important, obviously, when it comes to springs. The last variable that's important here is called the spring constant, and that is the stretchiness or stiffness of the spring. So we'll be referring to that as the spring constant. That's how difficult it is to compress or stretch the spring when a force is applied. Here are all the variables combined together into an equation known as Hooke's law. So here is the PhET simulation for springs. Here we set this. Okay, I'm going to set this mass to be 200 grams. And I have a ruler here ready to measure the change in length of the spring. So when I hang this 200 gram mass, it's going to cause the spring to begin oscillating, and the energy will eventually be dissipated, and the spring will come to its new rest length, which is shown here. With this information, we can calculate the spring constant of the spring. I can adjust the stiffness of the spring here, and you'll see that if I increase the spring constant, then the change in length is going to be smaller. If I decrease the spring constant, I'm going to have a larger change in length. So let's keep it somewhere around here. Okay, so how are we going to calculate the spring constant? Okay, so we need to first establish the change in length of the spring, which is going to be this length here. Right? We don't care about the initial length of the spring here too much. We don't care about the final length, although we can use those two values to find the change in length. What we care about is this delta x value. And using this ruler, it's approximately 0.32 meters. 32 centimeters on the ruler, I'm converting to meters here. Next, we need the force on the spring, and that force is going to be equal to the weight of this mass. The weight here is equal to m times g. The mass of this thing is 200 grams, so I'm going to convert that to kilograms. That's 0.2 kilograms. We're going to multiply by 10 meters per second squared for gravity, and so we get a weight equal to 2 newtons. And so because this mass is in equilibrium, the spring must be applying that same force. So the force from the spring is also 2 newtons. We can now solve for the spring constant. Hooke's law, the equation for springs is force of the spring is equal to K times delta X. If I'm looking for K, I'm going to rearrange my variables. K is equal to force divided by change in length. So our force is 2 newtons. The change in length is 0.32 meters, which makes our spring constant 2 divided by 0.32. 2 divided by 0.32 is 6.25. Newtons per meter are the units for the spring constant. Now that we have the spring constant, I can use it to make predictions about how this spring is going to behave under different amounts of force. So let's change this mass from a 200 gram mass to a 300 gram mass. And we should be able to predict what the elongation is going to be. So to do that, it's just a different set of variables. We're going to use Hooke's law again. F equals K delta X. This time I'm going to solve for delta X, which is equal to the force divided by the spring constant. So delta X, the change in length of the spring will now be the 300 gram mass is going to apply a force of 3 newtons. And the spring constant is 6.25 newtons per meter. So 3 divided by 6.25. And we get a change in length of 0.48. 0.48 meters. Let's verify that by placing the mass on the spring. Setting it to its final position, and we see the length is approximately 0.48. So now we can go ahead and do some practice problems with springs. So first question is, the spring in a scale in the produce department of a supermarket stretches 0.025 meters. That's our delta X value. When a watermelon weighing 1.0 times 10 to the 2 newtons, that's the force on the spring, 100 newtons. The spring constant for the spring is, so we're solving for K. K is going to be equal to the force divided by the change in length. The force is that 100 newtons. The change in length is 0.025 meters. Oh, I should do this again. Let me color coordinate this. So it's the force in the numerator, which is going to be 100 newtons, and the change in length in the denominator, delta X, which is 0.025 meters. So the equation is the force divided by change in length, which is 100 divided by 0.025, and 100 divided by 0.025 meters equals 4,000 newtons per meter. 4,000 newtons per meter, when written in scientific notation, is going to be choice 2. Next question. The accompanying graph shows elongation as a function of the applied force for 2 springs A and B. A is the one with the steeper slope. Compared to the spring's constant for spring A, the spring constant for spring B is, so here the axes are very important. Sometimes you will see this graph with force on the y-axis and elongation on the x-axis. In this case, it's swapped. So let's say the spring constant tells us how stretchy or stiff the spring is. If we have a large value for the spring constant, it means it's very difficult to stretch that spring. So to stretch this spring, let's say 0.2 meters, spring A is going to require a force of about 1.8 newtons. But to stretch it the same length, spring B is going to require a force of approximately 3.1 newtons. So spring B requires more force. In this case, the spring with the steeper slope has a lower spring constant. So the spring constant for spring B is going to be larger. Okay, next. The force required to stretch a Hooke's law spring varies from 0 newtons to 51.6 newtons as we stretch the spring by moving one end 5.88 centimeters from its unstressed position. Find the force constant of the spring. This force constant is the spring constant. So if they can refer to it as the stiffness, the stretchiness, the spring constant, the force constant. Usually it'll be spring constant. This is our K value. So let's see what's happening here. We have a spring. Let's look at it horizontally like this time. So say this is the unstretched, this is the rest length of the spring. And then a force is applied to it, causing it to stretch, let's say to here. The force acting on the spring here would be 0 newtons, that is its rest length. The force acting on the spring here is at 51.6 newtons. Which means, of course, the spring is pulling back with that same force. The change in length of the spring is our delta X value, and that is 5.88 centimeters, but they want us to provide the answer in meters, so I'm going to have to convert this from centimeters to meters. That's going to be 0.0588 meters. So our spring constant K, again, is going to be measured in newtons per meter. The force goes in the numerator, and that is 51.6 newtons. The elongation goes in the denominator. That's 0.0588 meters. And when we do this math, we get 51.6 divided by 0.0588, which is 877.6. 877.6 newtons per meter is the spring constant for this spring. Now with the spring stretched like this, there's of course going to be energy stored here, and we're going to address work, energy, and the energy stored in the spring in the next video.